Hello, my name is Michael Glinsky. I'll be talking to you about line VISAR measurements of energy deposition for next generation MagLIF laser preheat that are being done at NIF. The contributions are from my collaborators and co-authors at both Sandia National Laboratories and Lawrence Livermore National Laboratory. MagLIF is a magnetic direct drive ICF platform that requires coupling for the next generation of 20 to 30 kilojoules of laser energy into a gas pipe. That MagLIF starts by creating an axial magnetic field via azimuthal coils in the tens of Tesla range. Then you go and preheat the plasma with a laser to put it onto a higher adiabat so that you can reach thermonuclear conditions. That is the subject of the experiments at NIF. Then you drive a large axial current with the Z machine, creating a large azimuthal B field that compresses the target to thermonuclear conditions. More information about MagLIF can be found at these references. NIF is the only facility that can drive the full-scale next-generation targets. That the intended gas fill of the next-generation targets are about 5 milligrams per cc of D2. The NIF experiments use neopentane to achieve similar electron densities without the need for cryo, and also allows for the application of the axial B field because currently because of engineering constraints, you cannot both cool and apply the B field at the same time. More information about these experiments can be found in this talk at this conference by Brad Pollock. Here is the geometry of the measurement. You see the gas pipe with a quad of NIF coming in on this CAD-CAM drawing. There's a VISAR cone to shield the VISAR measurement from other stray light in the chamber. Here is a picture of the actual fabricated target. Here is the simulation geometry. You have a hydrocarbon gas with a laser that is deposited into it with a plastic window and an aluminum flyer plate around the edge. That it will be shown that VISAR is a direct measurement of the energy deposited, and this work develops the data analysis framework to estimate the deposit energy with uncertainty. Here are the parameters of the study. We did an ensemble of 400 hydrosimulations with non-LTE in the gas. Here are the base case dimensions of the simulation. There are 4 independent parameters. Here are shown the most likely as well as the range of the ensembles that were generated. Then there were 3 dependent parameters that were extracted from the results of the simulations when they were completed. This goes and shows the base case of the evolution. You see the main shock, and I'll show that in terms of the electron density, the temperature, as well as the radial profile. You see the main shock moving towards the aluminum flyer plate. And now I'll go and start the simulation. You see that there's an ablation of the inner surface off, driving this little shock to the outer edge. You also see the main shock now moving towards the aluminum flyer plate. It now has reached the aluminum flyer plate. The shock is now propagating, main shock is propagating through the aluminum flyer plate and has just now reached the outer edge. This goes and shows the energy budget as a function of time. You can see the energy being deposited into the plasma and then the transfer of that energy into the flyer plate from the gas. This goes and shows the main thing that is measured by the VISAR measurement, which is the velocity of the outside of the flyer plate. You can see the arrival of the initial shock coming from the ablation off the inner surface of the flyer plate and the arrival of the main shock. That is easier to see if you take the derivative of that velocity. This goes and shows the variation of the shock arrival times as well as the ringing of the shock in a spalled layer that I'll talk about a bit more in a second. This is a zoom in on the flyer. You can see that there's a spalled layer caused by a reflection of the shock into tension on the outside of the flyer plate. The thickness of this layer is different depending upon the energy, the laser and how it deposits the energy. Now I call your attention to this simulation. You see the ablation of the inner surface and this little shock that's being driven through the flyer plate and right now has just reached the outside surface. In a second, you'll see the arrival of the main shock. Here it is. It's just about ready to hit the inner side of the flyer plate. It's traveling through the flyer plate and just now has hit the outside surface of the flyer. For these 400 hydro simulations, you see the energy deposited plotted in as a function of the arrival time in a log-log space. You see there's a very good linear correlation in this log-log space, allowing you now to estimate the energy deposited directly from what this arrival time is, with about 1 nanosecond of uncertainty in the regression. This can go on and be transferred to the uncertainty in the energy. If you now add on the fact that you're not quite certain when the shock gets to that axial position, that the uncertainty is increased up to 2 nanoseconds. This can be corrected by using the first arrival time of this shock that's being driven from the ablation of the inner surface as a time judicial to reduce the uncertainty back down to this 1 nanosecond, which will allow you to estimate the energy to about 10%. That you can see here, this is the act that you can easily identify the shock arrival time on one of the interferograms coming out of the VISAR measurement. And here is an example of what the actual analysis will look like from another diagnostic. You can go and estimate with an uncertainty what the arrival time is of the laser as a function of the axial position. You can, from the previous interferogram, you can estimate what the arrival time is of the shock, correct it for this initial shock breakout time, then use this regression to estimate the deposited energy with uncertainty for the experiment, and then compare that to the Hydra simulation. So that the energy can now be deposited and be estimated with the between 10 to 20% uncertainty, that the pre-shock ablation of the inner surface wall surface can be used as a time judicial to reduce the time origin uncertainty. There are additional things to explore, such as putting a lithium or quartz window to stop the spallation to allow the use of the delta velocity to get a better estimate of the deposited energy, to put in a proper material model so that the spallation can be properly modeled, which it is not currently being done. You can also increase the radius to decrease the fractional error. We also need to model other experimental situations that we'll need to estimate the energy deposited from. And finally, you can use a Bayesian analysis to using all of the information to better estimate the energy deposited with a smaller uncertainty. Thank you very much.